Well, I Leetcode every day, never take no hiatus. This is number of sets of k non-overlapping line segments. Okay, let's go ahead and get right into this problem. So, given endpoints on a 1D plane, where the ith point from 0 to n minus 1 is at kx equals I. Find the number of ways we can draw exactly k non-overlapping line segments such that each segment covers 2 or more points. The endpoints of each segment must have integral coordinates. Okay, so you have to place lines at integer points, right? You can't place a line at 2.5 and 3.5, right? It has to be on 2 or 3, right? It has to be, the ends of the line have to be placed on integer points. The k-line segments do not have to cover all endpoints, okay? So there can be gaps in the space that you fill, and they are allowed to share endpoints, right? So if you had one line that went from 2 to 3, you could have another line that went from 3 to 4. So they can share endpoints, but they can't overlap, right? You can't have a line from 2 to 4 and 3 to 5, right? Because there would be overlap there, but you could have 2 to 3 and 3 to 4. If they share an endpoint, that doesn't mean they overlap. Return the number of ways we can draw k non-overlapping line segments. And since this number can be huge, we're going to return it modulo 10 to the 9 plus 7. Okay, so a little confusing. If we looked at this example here, and then, so we have 4 points, I guess you could call it 4 points in the system. What just happened? Okay, we have 4 points in our system. So I'm going to draw that system like this. So you could draw a line 2, 3, and 4. So this is our one-dimensional plane where we can put our strings. Are we calling them strings here? Segments, all right? I might use the term strings interchangeably, right? But you have these line segments. Well, if the dimension is 4, well, I could put a line here. That's one way I could do it, right? I have to put k equals 2 lines, right? Because we have k equals 2. So I could put a line here and a line here. That's one way I could do it. I could put a line of this length here and then another line of this of length 1 here. I could do the opposite, right? I could put a line. Oh, no, I couldn't do that. What else could I do? There's 5 ways of doing this. Okay, I could put a line here, here, and finally I could put a line here and here. Right, so these are all 5 numerable ways, right? So this is 2 lines, right? So there's a line here segment and another line segment here. 2 line segments on their own. Note that, there can be a gap. We don't have to cover the whole space just for this size 4 space. These are all, this enumerates all possible placements. Okay. So how do you approach this problem efficiently? Well, I guess what led me to the solution first was thinking about in this line segment system, right? I can place, if I have 2 lines I need to place, right? I can place the first line like this, and then for the remainder of the system, I have to put 1 line here. I could place the line like this, and then for the remainder of the system, I could put 1 line here. Or I could place the line like this, and then for the remainder of the system, I'd have 1 line here. So what I'm basically saying is, like, for any system, right, if this thing is length n, so let's draw it out. So we have this space, right, just in a general case. What I'm basically saying is we have this space, which is length n, right? And I have to place k lines. So I have to place k lines in this n space. Well, what are my options? Well, I could put a line of length 1 here, which means that I'm going to have to place k minus 1 lines here in this dimension here. There's something wrong with my iPad charger, unfortunately. Right? And I guess even more generally, I have to do k minus 1 lines here using what? Using n minus 1 space. Why? Well, because I create a line that's length 1 here. So then I have k minus 1 lines remaining, and I have to use n minus 1 space to do it. Okay, I could also put a line of length 2, but that means now that I need to put k minus 1 lines using n minus 2 space. Or I could do something of length 3, but that would mean that I'd have to place k minus 1 lines using n minus 3 space. And I could keep going down until I get to the very end using all n space, and I'd have to place k minus 1 lines using n minus n space. So I can, for any point, I can draw a line like for n equals 4 here, and I could draw a line that covers almost all the space. You know, I can draw a line that covers all the space. I can draw a line that covers this much and this much. So, and then I would just have to fulfill the remainder of the solutions for what's left over. Okay? Which makes sense, right? Because I could place a line, and then since I placed that line, I now have k minus 1 lines I still have to consider. And then for those k minus 1 lines, I have n minus the size of the line that I've decided to use left to fill that space. Okay? Now, there's one more thing I can do, right? I don't actually have to fill up all the space. So what I can also do is not fill up the space at all and fill up k lines using n minus 1 space. Right, so either I use a line, so I have k minus 1 lines left, and since this line has length 1, I have n minus 1 space left to fill it up. I could use a line that's length 2, so I have k minus 1 lines left that I have to place using n minus 2 space, n minus 3, minus 4, all the way up to n. Or I can decide that I don't want to put a line here, and I can just use k lines to fill up n minus 1 space, and that will, you know, create the space you see in this example, right? Like in the beginning, I can do a line of length 1, and then these are the ways that I can do a line where I use one line here in this system. Or I can decide to skip this space and not use it at all and distribute my k lines with n minus 1 space, right? Because here n equals 4, so I'm distributing all my 2 lines in n equals 4, but I can decide I won't use this space. So how many ways can I distribute a line in n minus 1 space? How many ways can I distribute 2 lines, k equals 2 lines in n minus 1 space? Hopefully that makes sense. So that's the idea here. So how do we generalize this idea? Well, let's just say that I have this dynamic programming array n, right? And I say, how many ways can I, using k lines, let's actually make this a different color. Make it red. So how many ways using k lines can I distribute those lines into n space? Well, I can distribute the line of length 1, right? So I can use this line here, right? I can distribute this line here, which basically means, well, I'm going to create a line of length 1, which will remove one space from the total space, right? Because when I use this one space, I've allocated it. So I have n minus 1 space available left. And since I've used the line, well, I can use d of k minus 1 because I've used the line. And that line uses space 1, so I have n minus 1 space left. Plus, well, I could use a line of length 2. And I get n minus 2 space left. Plus, d of k minus 3. So I can use a line of length, or sorry guys, I messed up here. No matter what, I'm using only one line, and that I could use a line that has length 2. I'm using one line, and that line has length 3. Dot, 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 all the way up to what? Well, I can't use a line that exceeds the space that I have. So the maximum line I could use in this example would be dk minus 1 n minus n. Right, so these are the lengths of all the lines I can use. So I'm basically saying if I have k lines, well, I can distribute one line, and I can make that line length 1. I can distribute one line, make that line length 2. I can distribute a line, make that line length 3, all the way up to n, right? Because the line can't exceed the size of the space that I'm using. And that will give me the total number of ways that I can distribute this system, right? Because what's basically happening is I distribute a line of length 1, and then my question just becomes, well, if I distribute a line of length 1, how many ways can I distribute a line of lines? How many ways can I distribute k minus 1 lines with in n minus 1 space? So that's basically the idea here. So if I distribute a line of length 2, well, I can do that. And then I would just have to figure out, well, how many ways can I distribute k minus 1 lines using n minus 2 space, since I've just used 2 space here. Right? And I would just solve that recurrence relationship for this problem as well. This is more stated in a tabular recurrence relationship. You could use normalization for this as well, right? Which might be a little bit simpler, but as we go through this problem further, we'll figure out that there's an optimization to make this even more efficient. Okay, so that's all the ways that I could distribute a line, right? These are all the ways that I could distribute one line, and these are all the links that I could use. Okay, now the final way I can do it that's not articulated here is I can also decide that I don't want to use this space for anything. So this is kind of like the outlier, right? This is basically saying, okay, I'll just distribute k. I'll use k lines in n minus 1 space. I won't use this space for anything. I'll leave this space empty. So the number of ways that I can distribute k lines covering n space is the same as the number of ways that I can distribute k minus 1 lines to n minus 1 space. If I decide to use a line of length 1, I can use the line of length 2, length 3, all the way up to n, or I can decide to not use this space. So I can also add in the number of ways that I can distribute k lines to n minus 1 space. Okay. Now, if you want to use a little bit of mathematical notation to kind of simplify the way that this works a little bit, we can call this the sum from I equals 1 to n of dk minus 1 n minus I. Right, so that addresses this sum here, right, because this sum has a very natural progression, plus, so this is one term on its own, d of k of n minus 1. So this is basically saying is all the ways that I can distribute one line in its length, plus not distributing a line at all and just not using this space. Okay, cool. So where do we go from here? Well, we can just do a for loop, right? A nested for loop if we went from for I in range n and for k, for j in range k. So we could populate this system I, or I guess ji equals the sum of I prime equals 1. I guess we could call it I prime. That's fine. I prime equals 1 all the way up to I dk minus dj minus 1 di minus I prime plus dj d of I minus 1. So we could run this whole thing, right? This formula here. Sorry if some of the notation is incorrect or sloppy. But the general idea is, right, we're going to have to look at O of n things here, O of k things here, and then here we have to do O of k, well, it's actually up to I, so O of n operations. Right, so for each O of n, so for each n we have to do k things, and for each k things we have to do n things, so that means we have to do big O of n times k times n, or big O of n squared k. Now, this might be good enough, but n is less than or equal to 1,000. So 1,000 is 10 cubed. So that'd be 10 cubed times 10 cubed times 10 cubed, 10 to the 9. So that's going to give us a time limit exceeded issue. So this is still too slow, right? Barely, but it is still the case that this is too slow of a process for our purposes. So I guess one thing we can do to fix this problem, to make it just a little bit more efficient so that we don't need to do O of n times k times n operations, right, is let's work with the math directly and think about how we can make this just a little bit more efficient. Okay, well, what if we could make this process here constant? Right? Meaning, when we calculate this is constant time, right? But this right now is taking O of n time to operate. So since it's taking O of n time, it's causing that additional n factor and making our solution 10 to the 9th. If we made this constant, then it would be O of 1. So if we just kept track of this sum somehow, then we wouldn't need to continue to recompute this over and over again. What if we had like a prefix sum idea? What if we had this information cached or saved somehow? That way when we calculate this information is constant. Well, let's call D of, call it big D of Kn equals one to n d of k the sum up to k n minus I. So that would mean if we substituted that in here, d of kn, so I'm just trying to do some direct substitution here, would be d of k minus 1 all the way up to n. Plus d of k n minus 1. So then you might be just saying right now, okay, well, that's just a foolish substitution. Who cares, right? I guess the idea here is then we could update this system. We could update dk of n by saying dk of n equals d of k minus 1 of n. Because what is dk of n in terms of dk of n minus 1? It should be small d here. All the way up to n. So if it's all the way up to n, then the recurrence relationship here would be... Sorry, this is a very confusing problem. And I'm not articulating what's going on here very well. And I apologize. Okay, because I guess the idea is here, because what is dk of n minus 1? Well, dk of n minus 1 is this. What's this? Ugh. It's this here. Just to prove it to you why I wrote this recurrence relationship like this. Right, it equals that. Let's make it blue. And we're adding in dk. Well, it's dk n minus I. dk of n. And since this is n minus 1, this would be n minus 1 here. So then we're just adding in this final term. Right, this is just the last term of this sum. This equals I equals 1 to n dk of n. Right, because this would be the final term of the sum if you just went one past what it was before. Right, so that's dk of n. Very mathematically intensive problem here. So with all that said, in order to solve this problem, if we just keep track of this sum using this system, then we only actually need to solve these two problems. And this can be solved in constant time, and this can be solved in constant time. And at the end, you just return the final value of this system. Hopefully that makes a little bit of sense. This is my own unique solution, and I didn't see anyone else do this, so it's a little weird. But that would basically make, now solving for any of these is constant, right? This is constant. This is a constant thing we catch. This is a constant thing we catch. Constant thing we catch. Constant thing we catch. Constant thing we catch. So for kn values, so in big O of nk time, we do constant things, so it's nk time, right? Now, what are our initial values? Well, in any space, right, d of 0 for any n value equals 1. Because for any k value, if you have, how many ways can you distribute nothing to any space? One way, doing nothing. Right, so that's basically what this is saying here. For any n value is 1. Okay. So let's go ahead and just walk through this recurrence relationship and see if it can get us to the solution. Okay, so we have big D and we have little d. Now we're doing kn. So we'll do 1 times n plus 0 for 0 times n for blank in range k. Okay. And then now let's just run through this recurrence relationship. So we'll go through n through k. So for nn in range, we don't need to look at n equals 0. For k in range k, we'll just update using this recurrence relationship and not think about it too much. So d of kn equals dk minus 1n plus dk n minus 1. Okay, so little d kn equals d of k minus 1 n plus d of k n minus 1. Let's okay, so this is dkkn dkk nn dkk nn, and then big D of kk and it updated is just taking the previous operations value and adding in current one. And then at the end, you just return D of -1, -1. Because this will give you, right, -1, -1 would be dkn, which will give you the number of ways that you can sum up using k things, right? Man! Alright, what am I doing wrong here? That'll be k because it's k plus 1. Oh, this is length k plus 1. Because that's in. Right. Let's see if this broke. My recurrence relationship had a k minus 1 nn. No, and that's wrong. It's -1. Why is it -1? Okay. So this is mod 10. We know this game. The game we always fail. Okay, so notice the max that this system can go to is n minus 1, right? It goes from n minus n, k minus 1, n minus n. You can't make a string that's n minus n here, because there would be no space for the remaining string. So the highest this can go is n minus 1. So this would be then n minus 1 here. So this would be n minus 1 here. And that gets you the solution. Alright guys, this may be my very worst video. If nobody watches this, like most of my videos, that's fine. But it's good for me for practice. This is it's difficult. Okay. What's the runtime? What's the space? Okay, so for space and run, it's the same. We have to look at n things, k things. So for all nk things, we do constant operation. That's nk time. We have to also populate nk things here and populate nk things here. So it's nk space as well. So nk time, nk space. Okay, see ya.